Hello, and welcome to Practical Defenses Against Adversarial Machine Learning. I'm your host, Ariel Herbert-Voss. Who am I? I'm a research scientist at OpenAI. I'm also a PhD student at Harvard University, and most of my work involves breaking machine learning systems that are deployed in real-world contexts. So this means that I look at the usual suspects like malware classification and image recognition, but it also means that I look at things like analytics platforms, recommendation systems, fraud detection, financial trading bots, etc. So basically anything that relies on machine learning as a core software component, I look at. And the content of this talk is the work has mostly been done in my capacity as a PhD student for a book that I'm writing for No Starch Press. So what is this talk? Well, 30% of it is me recounting experience in attempting to replicate attacks that have gotten the most press coverage. Spoiler, this means that adversarial machine learning in the real world is wildly different from academic research. Surprise. A lot of academic research around adversarial machine learning tends to focus on things like adversarial examples, which are extremely interesting and important as methods for probing our understanding of the dynamics of how machine learning systems work. But they tend to take up a bit too much air in the security conversation because they don't actually constitute a security threat beyond being yet another method for generating data points, which the model will mathematically misclassify. There exist other methods for doing this that are much cheaper and require much less math and are therefore much more attractive. The next 30% of this talk is going to be examples of attacks that I've seen in the wild in the last 5 years or so. The spoiler here is that facial recognition and malware classification are commonly cited, but there are more examples of financially motivated attacks against recommendation systems. The last 40% of this talk is going to be practical advice for defending machine learning systems. And this advice comes down to 3 recommendations that are centered on avoiding model leakage and bad inputs. So, what is wrong with adversarial machine learning? Well, most attacks that are proposed in the machine learning research literature don't actually work in the real world. And this is for a number of reasons. One of the big reasons is that university and research clusters tend to be different from deployment clusters. If you're working in a university environment, oftentimes you're going to do some sort of roll your own cluster adventure with using Slurm and MPI, and you get to work with some Byzantine university IT infrastructure. And your focus is you want to be able to demonstrate mathematically novel attacks, and that's going to be more important to you than things like reliability. So features that you'd find in an industry environment like managed cloud providers, containerization, continuous integration, those kind of things, those are all going to be more of a second thought for you. This additional layer of infrastructure that you find in industry changes the attack surface pretty significantly, and as such, it makes it really hard for literature around adversarial machine learning to apply itself to real-world situations. Another thing is that the artificial constraints that people kind of set up around developing these kind of novel attacks in the literature, they make it really hard to actually say anything about these attacks in the real world. It's possible to say something scientific about these kind of attacks, which is really important from a research standpoint, but realistically, most attackers don't really have constraints. They're not going to really limit themselves to a tiny epsilon ball around the decision boundary. They're going to do whatever gets the job done fastest, and they're going to do with the least amount of pain. So ultimately, this means that gradient-based attacks constitute a much smaller percentage compared to other less mathy and quick and dirty attacks. So roughly about 15% of attacks that are seen in the wild tend to be these gradient-based adversarial example kind of attacks. And so we're going to look at some of these less mathy, quick and dirty attacks as part of this talk. And I want to emphasize that these attacks are clever, but they're not necessarily complicated, at least in the theoretical sense. They require a basic understanding of how machine learning works, but they don't require specific knowledge of algorithms or models or any sort of specific areas of esoteric math. We can also distill these down to 2 types of exploits, where you have bad inputs and you have model leakage. So a sexy example of bad inputs is with self-driving cars. So last year I had a talk at DEF CON where I took some salt and I poured it on the ground because it was cold and it was in Boston, and I drove my friend's Tesla, and lo and behold, the Tesla started driving off into the sunset when it should not have been doing that. And then Tencent Keen Lab came out with a very similar report where they showed if you stick stickers on the ground, the Tesla will also interpret these stickers as a line and it will yeet off into the sunset as well. Should not do that, but it's very cool that it does. There's no need to generate any sort of bespoke adversarial examples for this kind of attack. You literally are just creating a physical artifact in the real world, sticking it out there, and the autopilot algorithm is interpreting it as part of the environment and then behaving accordingly. So it's the perfect example of bad inputs. I will say as a caveat, we have not seen this kind of attack in the wild, but the fact that we have done it on a real system that exists in the wild means that it is something that should be considered as like a reasonable example. An example of model leakage is with malware classifiers, with the Cylance endpoint protection bypass that Skylight Cyber had last year, where they showed that you can append a bunch of carefully selected strings to a malicious file and then fool the classifier into marking that file as benign. This required some reverse engineering to identify how the featureizer processes strings and then identifying which strings the model responds to best. So I'd say that model leakage kind of comes down to sharing too much information about the model to the point where somebody can either reverse engineer how it works, or as we'll see in the next tech, steal its functionality and use that to build bad inputs. Bad inputs and model leakage kind of go hand in hand together, much like fuzzing and reverse engineering in other software security contexts. It's kind of turtles all the way down, I'd say. So for this other model leakage attack, a really good example here is the email filters with that fantastic CVE in the Proofpoint email protection, which was maybe not so fantastic for the people who had to fix it. This one is really cool because the researchers collected scores from Proofpoint email headers, and then they built a surrogate model of the classifier that Proofpoint uses to identify phishing emails. And then from there, they were able to use the surrogate model to then craft malicious emails that will receive preferable scores. And this is very similar in the spirit of the previous one, but in this case, you're doing more of like a surrogate kind of model theft attack than you are doing like a reverse engineering kind of attack. But they both kind of fall under the umbrella of model leakage because they both require the person who built the system to have left out some information for you to pick up and use to reverse engineer or build something new for malicious use. Another example of bad inputs is with transportation prediction algorithms. This is a really great one. There was this artist in Germany who had this wagon full of 99 smartphones that were running Google Maps, and he ended up causing a traffic jam because the congestion algorithm that Google Maps uses to predict whether or not there's going to be a traffic jam, it treats each one of these phones as a discrete car object. And so if you have a whole bunch of them just sitting in a pile in a wagon, it's just going to interpret that as a giant, massive pile up. And then people are going to respond to this notification on their map accordingly, and then it's going to cause like a bigger issue, and you're going to get a jam out of that. So it's a really great kind of artsy example of a bad input kind of attack. It's non-traditional because it wasn't malicious. It was more just like a thought-provoking piece, but it's still like a really good example of some of the vulnerabilities that you find in these kind of systems that you might not have expected. And there could be, I could imagine a scenario in which somebody would want to do something very similar with a very similar type of system. Yeah. Another really great example of bad inputs is with recommendation engines. Recommendation engines have been around for a very long time. Like you've got Amazon. I'd say Google kind of counts as a recommendation algorithm because it's recommending you search results. As long as these kind of products have been around, Black Hat SEO has been around, and that's all about trying to use things like click farms and review farming, depending on if you're like Yelp or Amazon, to try to pump up your product or your link or whatever it is when the algorithm is trying to downrank you. And it's very much a cat and mouse game. It's been played for a long time. I'm not going to go too much into the details there. And if you're in the industry, like you're already probably pretty aware of this wonderful cat and mouse game. But it's a really good example of bad inputs and some of the harms that come about from not thinking too clearly about where you're getting data from. I guess a contemporary example of this is during this coronavirus outbreak, I've been doing a lot of jigsaw puzzles, and I found this one jigsaw puzzle that was on Amazon, and it was of the, I forget actually what it was of. I think it was of the baby Yoda, and it was definitely a Chinese knockoff, and I was very excited because it was very cheap. But when the puzzle actually came in, and it also had really good reviews, and I was still kind of sketched out by it because it just didn't look that legit, and the reviews were all kind of the same copy-pasted thing over and over again. And I get the puzzle in the mail, and I open it up, and like half of the pieces are missing the backing. It's just a total mess. And then trying to report it and send it back to them, it was just kind of a huge hassle. But it's a really great visceral example of how recommendation engines and bad inputs are something that we still kind of face today as like a kind of low-level attack kind of situation. Another example of bad inputs is with trading bots. So I had this project a few years ago where I was called in for this. They were a trading bot cryptocurrency startup. They had these bots that they'd pull in information from Twitter and some of these financial crypto forums, and they would use that information to make predictions about what the price is going to be, and then they would make trades based off of those predictions. And they called me in because they were noticing that there were some weird behaviors about the prices. They noticed that they were kind of changing in a very regular way that just doesn't seem realistic. So we did some digging, and we found out that some people were kind of flooding the hashtags that this bot was using in its sentiment analysis engine to convince the algorithm that the price needed to go up because people were talking very positively about this cryptocurrency coin, which is now no longer with us for good reason, probably. So this is another great example of bad inputs because they weren't sanitizing anything. They were just kind of pulling straight from Twitter, and they weren't really thinking through what could your threat model be around somebody who might want to make money off of your poor bot design. Another example is with fraud detection of model leakage specifically. If you work in fraud detection, like you know this space. But my favorite example of this is there was this attack, I want to say it was like 2 years ago, where there's this group that they made a bunch of fake apps that weren't monetized, and they deployed them on the Android store, and they were just like very basic apps. You just click through and just push a bunch of stuff. And the whole point of these apps is that they're just collecting kind of how you're scrolling through stuff and how you're clicking on things and timing and whatnot. And the whole point of this is to sort of train a secondary model that can approximate that kind of behavior. And then the idea is you then deploy that model on a set of ad monetized apps. So that way you don't need to sort of do content or user farming if you're running some sort of scheme like this. You can just literally run this model and it will generate revenue for you, and you don't have to do that much work. It ended up getting detected. It was phenomenal. But it was a really good example of model leakage because in order to execute this kind of thing, you need to have some idea of how the Android store or whatever app store you're using does like some sort of bypass or does its ad fraud detection. And most of these things, they all use machine learning because everybody loves machine learning for like detecting this kind of stuff because it's usually like a pretty good like first pass for if there's something that should be flagged. So that was a whirlwind tour of 7 different kind of attacks that we've seen within the last 5 years. They're not as sexy as you might expect, but they definitely still count as attacks. Machine learning is something that's very popular these days because it's something that people seem to think is going to give you a lot of business revenue. That may or may not be true depending on what industry you're in. I'd say that like, depending on your industry, you could probably make a decent amount of money. There's probably other situations in which you don't necessarily need machine learning, but all that to be said, the more popular that machine learning gets as a tool to use for business analytics, the more popular it gets to be a target for people to focus on trying to make money off of the exploitation of these kind of systems. So I have here a list of 3 defenses, more or less, that will cut down on like issues that you will have by about 85%, which is pretty cool. So the first one is you should use block lists. So the example that I shared about the trading bot is the way that we fixed that issue, and we were able to fix it like 100%. We just used an allow list for information sources. So we didn't just pull from random, we pulled from a couple of different things, and there was a human in the loop whose role it was is to make sure that things are moving slowly. I think a very important part of developing a machine learning system that is robust to issues with bad inputs is to make sure that you at least have some sort of human in the loop kind of interaction, because that lessens the chance that you're going to find something, or that you're not going to, it lessens the chance that you're going to miss something important, because at least you have human reasoning ability around like these very nascent AI systems that are not quite ready yet to be out on their own doing this detection work. So the second defense here is you want to verify the data accuracy using multiple signals. So an example is for a facial recognition system, we saw a 75% reduction in adversarial example-induced false positives when we use 2 camera sources instead of 1 for identification. This percentage increases when the 2 cameras are farther apart. So if you're familiar with Byzantine fault tolerance and distributed systems, this makes sense, because if you have multiple sensor sources or like multiple nodes, it's harder for a malicious or faulty sensor, oftentimes you can't tell the difference, to fool the consensus algorithm into accepting a bad decision. And this is especially self-evident in self-driving cars, which tend to use a decent amount of sensors, so that if one of them ends up either breaking or if it's getting bad input, at least you have a couple of other ones that you can rely on, and they'll all kind of communicate and sort of decide what the reality outside of the car is like. So the third defense is you want to resist the urge to expose raw user statistics, or raw statistics to users. There is always going to be a trade-off between providing interpretable predictions and providing enough information that an attacker could reverse engineer your model. There's a lot of conversation around the importance of having interpretable predictions, because it's understandable. You have this black box model, you kind of want to understand what it's even doing. But at the same time, if you give too much information about what it's doing, it makes it really easy for people to figure out, like, okay, given that it's responding to these pieces of information with these numbers, I can probably pump up these numbers for this other piece of information using this extra thing. So it then becomes kind of its own attack vector in its own right. So one of the most surefire ways of handling this, because it is a trade-off you can't really get rid of, is you want to round your statistics. This tends to reduce the ability to reverse engineer models that are deployed on certain cloud API services by about 60%, based off of some research that has been done by me. So in conclusion of all of this, the methods of exploitation for ML systems are very similar to traditional software. In practice, we see two categories of exploitation. We see the bad inputs, examples with the self-driving car stuff, with transportation prediction, trading bots, recommendation engines. And on the other side, we have model leakage, which really tracks with the malware classification example, email filters, and fraud detection. There's a lot of taxonomies for categorizing potential attacks, but in practice, we tend to just see these two categories, which is pretty interesting. And as I mentioned earlier, bad inputs and information leakage tend to enable like model reverse engineering, and also like building surrogate models so that you can do bad things with it. And not only could you do bad things with it, but you could also use that to kind of steal somebody else's IP, which is problematic if you have some sort of proprietary solution that like is your workhorse for your company, which is, you want to protect that. So you want to make sure that you're not giving out too much information so that somebody can reverse engineer it. So based on what we've seen in the wild and our own experiments, about 85% of attacks on ML systems can be mitigated with these three recommendations, which I will reiterate again. You should use a block list, you should verify the data accuracy using multiple signals, and you should resist the urge to expose raw statistics to users. And that is what I have for you. Please reach out if you have questions, or if you hated this, or if you have feedback, or if you want to know more. My DMs on Twitter are open. I'm at Adversarial, and you can also send me an email at adversarial@openai.com. So thank you. Hello. Welcome to the Q&A. I'm not sure what I should be doing here. Yep. Oh, okay. Cool. I think I've mostly been answering questions in the chat. So it's okay, cool. Well, Gabriel had a really good comment where he said that several years back at B-Sides Las Vegas and Ground Truth, the general theme was using people and ML to complement each other rather than replacing one with the other. And I just wanted to say that I really like that. I think that it's really important to remember that humans kind of need to be in the loop, because for the most part, ML systems aren't really ready to kind of be out doing automated stuff on their own. Let's see, there's also another question. Oh yeah, so Gabriel also asks, did you happen to see the Attacking RL AI talk earlier today? And I did not see that, but that sounds great. Would somebody be willing to kind of give me like a link to it, and I'll take a look, because that sounds pretty rad. Oh boy. Also saw the question about fully homomorphic encryption. I have some thoughts about that. I don't know how familiar people are in the audience about differential privacy, but so far that is the only approach that I've seen with cryptography that has anything of use for machine learning stuff. I think there's some use for some some sort of more complicated encryption methods, but for the most part, I'd say that those things are kind of overcomplicated. You're taking like, I mean, cryptography is already extremely computationally expensive, and so is machine learning. And so you're taking one thing that's very expensive and then throwing something else that's even more expensive on top of it. It often doesn't work out as well as maybe you would hope. So I imagine that there are some use cases for it, but I can't imagine any off the top of my head. Let's see. Ooh, okay, good question. Are there open source projects you recommend that are conducting AI attack defense R&D? There are. So the first one, there's this repo that some Googlers made. It's called Clever Hans, and it's really great for looking at how to do gradient-based attacks against neural networks specifically. There's also a few other resources. That one also hasn't been updated too frequently recently because, as I said earlier in the talk, gradient-based attacks aren't really something that people see a lot of. That said, there's another one that I've been following that's called SecML. Let me see if I can pull up a link to it. And I believe that it's a group of Italian researchers who have been putting this together, and it's pretty solid. Let's see. Maybe I should focus on questions first, and then, yeah, let's see. Ooh, good point about the partial homomorphic, working with much lower latency. That is a good point. But still, it's partial and it's still kind of expensive. And I haven't really encountered any situations whereby anybody has asked me to implement this after I have given them kind of the layout of how expensive it would be and how much accuracy you lose when you use encryption methods. A question about the Google's federated learning. I think federated learning is underappreciated, but I think there's also a tendency to ignore the fact that there's a decent amount of other concerns that we have around the security of those things. Federated learning is really cool, but you still run into all the issues that you have with distributed systems and Byzantine fault tolerance kind of questions. So I'd say that it's still very new technology, but there's a lot of potential for it. And I'm personally quite excited for it, especially since everybody's very excited about enabling edge compute, especially. Oh, yeah. Good point about the IBM Adversarial Robustness Toolbox. That is also a great resource. Also, somebody said incomplete data can be, William says that incomplete data can be used to bias conclusions, and that is definitely true, and we have seen that happen. That's something, machine learning is kind of an old field, and a lot of the same security questions that we have around these new things, like using it for malware classification and image recognition. A lot of these kind of questions about inputs and outputs and cleanliness of the data have been around for a long time. And the question of bias is now a little bit more in the forefront because I guess now our systems are more connected to the socio-technical aspect of society, I suppose. Yeah, I'm sorry if I'm not entirely answering all these questions. This is kind of a weird way to do question and answer. Yeah. If you have more specific questions and I haven't answered something specifically, or maybe I rambled a little bit too much, definitely feel free to reach out to me on Twitter. Like I said, my DMs are definitely open and I love talking about this stuff, so I'm more than happy to talk about this stuff. And also you can send me an email, which is adversarial@openai.com. I also answer those. Okay, so Fernando asks, any other InfoSec vendor examples beyond Cylance and Proofpoint? Those are the two that spring to mind because those are the two that have at least captured journalism attention. I think if you were to ask people who actually work inside this space of malware classification, you'd find that there's been a lot of examples of people trying to craft things that will sort of trip the filter. And there have been a couple of open source competitions around that too. In the AI Village at DEF CON, there is a competition sort of running with Hiram Anderson and his team about trying to develop ways to kind of fool and also defend machine learning systems that do malware classification. And that's kind of been a lot of his work too. So you can see some of the competitions that he's proposed in the past and also some of his work. I'm a huge fan. So somebody asks, does the improvement of deepfakes make this harder now? I think that deepfakes are sort of different. I think deepfakes have a huge potential for doing bad things and making it easier to do social engineering for sure. And I think that there were a couple of talks earlier today that kind of address this kind of thing. But as for making it harder for or easier for people to do like attacks against machine learning systems that are more like fundamental, like malware classification or any of those things, I don't think deepfakes play as big of a role in that. But that said, so with the so I work at OpenAI, and one of the things that we've produced is this GPT-3 language model, and it's very good at generating text, and it's also very good at generating fake code. And there are a number of things that we're currently actively looking at in order to make sure that people like don't completely misuse these kind of things. And when inevitably they do, we have some detections in place, and we have methods for handling these and triaging these kind of situations. And I'd say that synthetic, and all this to say that synthetic text, synthetic images, those kind of things, those all definitely have a potential for misuse. But I don't think they're necessarily as relevant to breaking adversarial machine learning or breaking machine learning products. I think maybe the closest thing is if you're trying to generate a bunch of text to fool a spam filter, then something like GPT-3 would be very good for that, but only up to a certain point, because that attack only works so well, and it depends on how well you build in your defenses and how well you sanitize like your inputs, so to speak. All right, so I think I found the that thing that I mentioned about open source projects. Here's the one I was thinking of. And a couple of other people have mentioned other really good ones too to check out. So check out the chat for other things that people have shared. Ooh, so Benjamin has a really good point here. He says, I think there is an argument to be made that larger, more complex models, like those used in generating deepfakes, are easier to do gradient-based attacks against. I would think larger models would be more robust to model leakage, but don't have a strong prior there. Yeah, this is a really great point. Given that deepfakes are fundamentally using GANs and you're generating images, they are definitely more susceptible to gradient-based attacks, but it's unclear. Let's see. So there was the deepfake challenge that Facebook put on. It was really cool. And there's sort of some overlap between generating deepfakes and generating ways to detect deepfakes and ways to get your deepfakes to kind of fool deepfake detectors. And all of that is sort of like turtles all the way down, but it's all very relevant. And that's a context, one of the very few contexts in which I think that gradient-based attacks are extremely relevant. So 10 out of 10, I agree with that. As for the larger models being more robust to model leakage, that's also sort of intuitively true as far as we've been able to see. But we're actively doing some research into seeing how much the scale of the model is impacted by things like the secret share attack or some of these other kind of attacks from the literature that are still very relevant at some point, but they're not quite relevant yet. And we haven't seen anybody try to use any of these. Right. I've been told that I can leave. I'm not sure I want to leave yet. So if there, okay, I don't have to. um, yeah, so I guess if there are any other questions, this is kind of an unnatural way of answering questions. And I am aware that my responses are a little bit disjointed. And I would eagerly like to have more conversation. So please reach out to me, either email, Twitter. Those are the two things that I answer. I'm not very good at answering other things. Yeah, I suppose with that, I can leave. Although, hold on a second. Fernando has a question. Isn't model leakage just an issue of not showing internal scores? And the answer is yes. For the most part, that is exactly what it is. It's just like standard kind of trying to prevent people from reverse engineering your stuff, or at least making it harder to reverse engineer your stuff. You don't want to share any sort of information that makes it easy for people to figure out what it is that you've done. And that's not to say that you should rely on the security by obscurity rule, because we all know that that doesn't work. But it is good to be prudent about whatever information it is that you are sharing. Okay, and with that, I will leave. Thank you very much for coming to my talk. I hope you enjoyed it. Please reach out, please. Cheers.